Cool. So most of you have met me. My name is Luca Matra, and I'm a submillimeter array fellow, i.e. a postdoc at the Center for Astrophysics and at the SMA. And so the goal of these two kind of tutorial lectures is to get a sort of a real practical view of what the data really looks like after all of this thinking about what interferometry is and what our data looks like in this mathematical view. I really want to give you a more pictorial view of what the data really looks like. And to begin with, we're going to start with some non-imaging analysis. So basically, you've in the past two lectures, you've ended up with a calibrated data set that you calibrated in Mir. And before you even go into imaging, you can basically deduct what your emission may look like just from looking at the visibility function. And I'm going to guide you through some of that. And so the key now is, because we're living in UV space for the next half hour, we're going to put on our Fourier glasses, and we're going to work in this UV space that you've seen already, where the units are kilo lambda, so thousands of wavelengths. And every point, this is just a recap, every point in this UV space represents one baseline at a given time, at a given frequency. And so, for example, if we choose this point, it's a given baseline. And to turn the meters of the baseline into kilo lambda, I basically just divide the baseline by the wavelength of the observation, which for 230 gigahertz observation is 1.3 millimeters. So practically, if I have an SMA baseline of 13 meters, where that point will go here is at 10 kilo lambda. All right, let's start. So you've seen this before. This is the Van Zittert-Zernike theorem, which basically tells us that what we're measuring in reality is the visibility function with an interferometer, which is the Fourier transform of the sky image, which is what we want, or where our brain usually works. And vice versa, the image is the inverse Fourier transform of this visibility function, which is what we measure. And just to go to, again, just to brush again on the very basics, I don't think the Euler formula has come up yet. So this basically is a complex representation, because the visibility function is a complex function. So it has a real and imaginary part, or equivalently, an amplitude and a phase in this Euler representation, where C is the amplitude, phi is the phase, and the real imaginary part are C cos phi and C sin phi. Okay, so at any time you have basically, you have a function, you have the real function, the real part of the visibility function, and you're going to have an imaginary part of the visibility function in this UV plane. All right, so what does the calibrated data set actually look like? So what we're going to have at the end of all of that nightmare of a calibration, we're going to have a big table of UV coordinates, U and V, of endpoints of UV coordinates. They're the real part that we measured of the visibility function, and the imaginary part that we measured of the visibility function, and the weights that Carto mentioned, which are related to the uncertainty on that measurement at that UV point, as weights are 1 over sigma squared, where sigma is the uncertainty. Cool. So at every point here, every point will have its own real part, its own imaginary part, and its own weight. So it's just a big table. And N is basically the number of baselines, which is the number of antennas. You've seen this formula before. It's basically all the combinations of possible baselines that you can have. Actually, you've got, I think, twice that many points, because as David said yesterday, because the sky brightness distribution is a real function, in Fourier space, when you know a point in UV, you also know what its real imaginary part is in minus U minus V. It's the same. Okay, so it's the function is symmetric. All right, so again, I'm just going through this again so you know what I'm talking about when I go into the next step. So as David showed us yesterday, our Fourier pairs. This is really, if there's one thing you have to take away from this, is these Fourier pairs. The point source, or i.e. a delta function, mathematically becomes a constant in the real part of the visibility function. A small Gaussian becomes a big Gaussian when you Fourier transform it. Uniform disk goes to a Bessel function, inclined Gaussian goes to an inclined Gaussian, but 90-degree rotated, because the broad part becomes the narrow part, and the narrow part becomes the broad part, as you would expect. Now, if the source is symmetric and centered at the origin, the phase is 0 everywhere. So here I didn't show phases, but the phase is 0 everywhere here, and also the imaginary part will then be 0 everywhere. So if the source is symmetric and centered at origin, the phase is 0 everywhere, and the real part is the same as the amplitude. This is just mathematically, if you write down Euler's formula, you get this out right away. So the amplitude tells you how much flux there is, and the phase tells you where the flux is in the image, as you've heard before. Now, just a reminder that we have a UV coverage. So this ideal perfect visibility function, we are sampling it at discrete points in UV space. So it's as if like you go to this point and you're like, okay, what's the value of that function, of that 2D function at this point? Okay, so we have a sampled visibility function. And so what happens if the source is not centered? The phase, so if the source is centered, the amplitude will look like a big Gaussian in this case, and the phase will be 0 everywhere. If you offset this Gaussian, the amplitude will be exactly the same because the amount of flux in this Gaussian is the same as here. But the phase will look different. It will look different. What it will look like wraps that are in the direction of this offset. So this offset is in this direction, and so the phase is wrapping in that same direction. And this is because of the Fourier property that an offset in image space is a phase shift in UV space, which produces these wraps. And once again, you can literally plug in the numbers here, and you will see you will see this. So I encourage you to do it at home to just convince yourself of what's going on here. Okay, so what we're going to do now is I made a Jupyter notebook where we're going to throw some kind of example visibility functions that are sampled by an observatory, and what we may and how we may be able to interpret them before we even go into image. So, all right, so we're going to open the Jupyter notebook. Okay, hopefully this works in real time without much lag. By the way, all this will be available to you, so you can open this notebook at your own in your own time and play with it, change the values, and all that. I hope you can see. Okay, so here we go with this tutorial. So again, the point is to help you kind of picture what this sample visibility function looks like and how you may be able to interpret data just by looking at it. So the first thing we do is we import some, and I'm going to run this in real time. So we're going to import some Python packages, and that we're going to need later on. And what we're going to do is we're going to open a real data set. In this case, it's an ALMA data set that I got like 2 years ago, containing observations of the nearby star Vega. So you may think, okay, it's a nearby star, so a star is very small, it's very far away, so it might just look like a point source. Now I did do a trick, so I increased its flux the real flux of the star, 1.3 millimeter, is 2.5 millijansky. I increased that to 100 to make things clearer for you. And you import this exactly as I said, as basically just a big table of UV, real, imaginary, and weight. So that's what I'm going to do here. I have a NumPy save file where I've got all of my visibilities saved, or this big table that I said. And I'm going to read it in. So UV, real, imaginary, and weight is basically loading this big table. And so in each of these arrays, I will just have a column containing all of the values for these numbers. So in practice, it's very simple. It's just a table of values. It's not scary at all. All right, so we're going to plot. The first thing we're going to do is we're going to plot. I'm just plotting U versus V. Oh. I pressed the wrong button. So the first thing we're going to do is we're just going to plot U versus V. And that will give us our UV coverage, which is what I've been showing you. And you can see this UV coverage is kind of different from the kind of roughly circular symmetric thing that you've seen before. And this is because so it's very elongated in the east-west direction compared to the north-south direction. And this is interesting. So I'm going to point it out. So this is because the star Vega is very far north. It's at plus 40 Dec, and was observed by ALMA, which is in the southern hemisphere. So the star basically only went very little above the horizon. So it did this basically in the sky in the north direction. Let's say north is there in the north direction. And so what happens is that the baselines that are along north-south, so along this line, looking at the star, basically are looking very low down. So the projected baseline is very short. And this is why this looks very squished in this direction. Whereas a baseline that is east-west and is looking at the star, which is there, is basically like it doesn't matter at what elevation the star is, the baseline will be the same all the time. And so that's why this looks elongated in that direction. Okay, so we got a UV coverage. And so this UV coverage, so with the color here, I'm just putting ones everywhere. So the color is just the same everywhere. Now there is some level of transparency that I put in here, which you may or may not notice. So this stuff is more transparent than stuff here, because here the points are denser, which is what David was saying yesterday. At the shorter baselines, the points are denser just because the Earth's rotation smears them out less. And okay, so north-south projected baseline are very short. And now what we're going to plot is so we have seen this UV coverage many times, but just with ones at every point. What I'm now going to plot, I'm going to use the color scale to represent the real and imaginary part of the visibilities. So I'm gonna run it. So don't be scared by the code. Most of the code is actually plotting. We're not doing very much. So, but you can play with it yourself when you get home. So here's the real part of the visibilities plotted here. So the color scale now is, oh no, press the wrong button again. So the real part here is plotted in millijansky in the color bar. And what you can see in this data set is that basically everywhere in UV space, the values that we have for the real part of visibility function is somewhere around 100. So this should tell you, without making an image, that what you expect your emission to be is a point source, because a point source is a constant everywhere in UV space. All right, and if I go down, and now I plot the imaginary part, now this has noise. The noise, you can't really see much noise here because I made the star very bright, but you would be able to see it if I didn't do that. So you see the imaginary part is at around 0, which is what you expect if the star is well centered at the face center of our observations. Okay. And what I've also plotted here is the weights, which we also have for every UV point. And you can see that these vary in various parts of the UV plane. For example, if you look at these tracks, so these tracks are, these different points are different points in time. And so you can see that in this case, the weight went up, which means that the weather got better. So if the weather gets better, the system temperatures go down. And if you remember the formula from Cardo yesterday on how to calculate the weight goes up. So the weather got better, so the weight of the visibility went up because it was less noisy at that time. Okay, and the other thing you can do,
how much changing elevation?
Oh, I don't remember. All right. I can check though.
That could also change system temperature.
Yes, thank you. That's right. Very good point. The other thing you can see here is that the weights change between a value of 0.01 per millijoule squared to 0.07 per millijoule squared. And I told you that the weight is 1 over the uncertainty squared. So if you do 1 over square root weight, you get about the uncertainty of each of the real and imaginary part of each of these points. And this uncertainty, if you do 1 over square root weight, will be about 4 to 10 millijansky per UV point. So there would be a noise level. There's a noise level or an uncertainty of 4 to 10 millijansky in each of these points. And this is exactly why I made the star 100 millijansky so that you could see it in this plot up here. Because if the star was only 2.5 millijansky, you would see 2.5 millijansky everywhere in this plot. But because the noise is 4 to 10 millijansky, the star would be buried in the noise, and you would have been able to see it here. You would just see noise. All right, so one thing you can do to decrease the noise level is and judge how much emission there is at short baselines versus large baselines. This is something that Mark showed you earlier, is make a useful plot of the real and imaginary part of the visibilities as a function of UV distance. We want to basically make a radial plot. So what we do is we basically draw concentric annuli, and we average all the points within these annuli, and we obtain one value per annulus, and then we plot these values of the real and imaginary part as a function of UV distance or UV radius, or whatever you want to call it, which is just the quadratic sum of U and V. Which is equivalent again to averaging azimuthally in UV space. All right, so we're going to do this. I'm going to do this live. All right, and this is what we get. So this is the real part. So as we kind of expected by just looking at in 2D, the signal, the real signal, is constant as a function of UV distance in kilo lambda. So this confirms that we're probably looking at a point source. And once again, then we look at the imaginaries with real uncertainties. You see that the imaginary is consistent with 0 at all UV distances within the error bars, which means that the star looks like is well centered in our data. And what you may notice is that the noise goes up as you get to longer baselines. So these points at longer baselines are more noisy, have larger uncertainties. And this is because in our UV coverage is more sparse out here. The density of points goes down, so you're averaging over fewer points, and that's why it gets more noisy. And this is why when you want to wait before imaging, you may want to use uniform imaging to basically increase the weight of these visibilities compared to these ones. Because naturally, with natural weighting, these would weigh more than those. Okay. So you would conclude is there is signal strongly detected in the real part of visibilities at around 100 millijansky, and it's mostly constant with UV distance. The imaginary consistent with 0 everywhere, so source is consistent with being symmetric and centered on the phase and pointing center of our observations. So as I said, the UV analysis alone indicates the presence of a point source in the center of the field with a flux of about 100 millijansky. And this just comes from looking at the UV data. Obviously, this is the simplest case of a point source. But okay, let's go a little bit harder. So let's move to an offset point source. So I'm gonna manually inject an offset. So an offset in image space, remember, is a phase shift in UV space. So I can manually add a phase shift in UV space, and I'm gonna run this, and I'm gonna pull up the UV plot again, showing the reals and the imaginaries. And here we go. So this is what the reals look like if your source is offset, if your point source is offset from the center. Now we have applied let's see if I have it still. I've inserted a phase shift. So basically the real has now a cos phi term, and the imaginary is a sin phi term. And so again, you can do the maths very easy. So you end up with a real part that is basically a cosine. And so if you look at the color scale, this is basically following a cosine in this direction. And the imaginary, as you may expect, instead follows a sine function. So at the origin, this is 0 for a sine function, and it's maximum for a cosine function. And so what can we learn if we see something like this? So we see a wave in the u direction, which means that the offset. What did I tell you earlier? That this wrapping, this cosine function follows the direction of the offset. So you can deduce just from looking at the fact that these lines are vertical, that the offset is in the right ascension direction. So along the x-axis on the sky. And then you can figure out how offset is the point source. So how far is it from the phase center? And you can do that by just looking at the period of this cosine wave. And the period turns out to be the inverse of the on-sky offset. So if we measure it for this exact case that I fake injected, you find that the period, so from where it goes from, let's say 0, which is maybe the color scale is not the best, but from 0 to 0 again in one full cosine cycle, it looks like this period is about 70 kilolambda, right? So the offset is 1/70 kilolambda in radians. And if you turn that to arc seconds, you find an offset of 3 arc seconds along the RA direction, which is exactly what I injected myself. But if this was data that you didn't know what the offset was, you could derive the offset directly from just looking at these wraps, if your source is bright enough that you see this above the noise. Okay, so what would happen if instead of the offset, instead of being along the right ascension direction was along a 30-degree a line at a 30-degree angle from the x-axis? Again, I can insert this offset. And again, as I said, you can play with this, change the offsets, change the direction, and see how this changes. And now the offset is along the 30-degree direction. And this is the direct consequence of a Fourier property, which is if you rotate the image, you get the same rotation in Fourier space. Okay. And the same for the imaginary, except it's a sine rather than a cosine. Great. Now let's go one step further into a slightly more complex, but still very simple morphology, a ring morphology. So now some of us, like me, observe a nearby star to look for circumstellar disks that typically look like rings or belts of comets and asteroids around nearby stars. And that's a very simple ring morphology. And so we would expect the emission to look like a ring. And so now we're going to use, instead of looking at real data, we're going to play with it. We're going to make a model that is just a ring. And we're going to use Python's fast Fourier transform. So the fast Fourier transform is not this very scary thing. It's just a function that you can write in, you can use in that you can take from one of Python's packages, and it's a one-line thing. So it's very easy. So you can play with it. So let's make a model ring. Here it is. I'll run it again, but here it is. So here it is. I made a model of a ring that has a radius, it has a width, and it has a total flux in millijansky. So the integral of the flux everywhere here. And I want to know, what do I expect the visibility function to look like? And you can do this for any model. You can make any model you like of whatever you might expect your source to be. And so now I'm going to use NumPy's FFT routines to see what its Fourier transform looks like. Oh, spoiler alert. And here it is. It's a 0th order Bessel function, which is what you would have expected analytically. And actually, this is treated in the book that you've been advised to check out. But you can play with this in Python very simply. And so you've got a 0th order Bessel function. And what we can do is we can check out, again, it's azimuthally averaged radial profile. So again, we integrate in concentric annuli and we make a radial profile. Here we go. All right. So now the data has no noise. It was just a model, so it has no noise. But this is what this looks like when you average. And so what can you get from this? So if you're someone like me who looks at nice rings, you may use this to infer properties of the ring in image space without ever doing any imaging. In particular, and the imaginary is 0 everywhere because I put the ring right in the center. And the ring is symmetric. So as expected analytically, the real part of the visibility function for a ring is proportional to a Bessel function of 0th order with the x of the Bessel function being 2 pi r q, where q is this UV distance. Okay? So we know that the Bessel function has its first zero, so its first null, which is what Mark mentioned earlier. So the location at which the function crosses zero at a value of x of 2.4048. That's just how the Bessel function works. So we know that for a ring, the first zero of its real part of the visibility function should be located at 2 pi r q equals 2.4048. So we can use the location of the first null to tell us the radius of the ring, because r is the radius of the ring in arc seconds. So we can use the UV distance of the first zero, which in this case is 19.7 kilolambda. Let's go back up. Yeah, it's about 19.7 kilolambda here where it crosses zero. There's an unfortunate line in the screen. You can use the 19.7 kilolambda to derive a ring radius of 2.4048 divided by 2 pi q, which would give us 4 arc seconds. And that's exactly the radius of the ring I put in my model. So this is basically just to give you an idea of how you may very easily make a model and Fourier transform it and then compare it with your data. Now, the one step we didn't do here, so if you wanted to fit, I don't have time to go through this because it's half an hour already, but what you could do directly in UV space is you could make a parameterized model of what you expect your source to look like. In my case, a ring. In your case, a Gaussian. I don't know. In your case, a point source. And just like I did, you can Fourier transform it to obtain your ideal visibility function. In the next step, of course, we know that for interferometer, this visibility function is sampled at discrete points. So you would basically evaluate this model function numerically by, for example, interpolating at the location of the visibility points that you've measured. And then you would compare these model real and imaginary values to your data real and imaginary values. And then you can basically look at the residuals, calculate the chi-squared, minimize the chi-square and find the best fit model. And therefore, you can carry out your fitting directly in UV space without ever the need to look at an image. Now, this is all great, but in practice, all right. And so before I go into that, what I want to say is that doing this analysis in UV space accounts for the inevitably missing short spatial frequencies. Remember, there is always going to be a hole, as David said yesterday, in your UV coverage. And if you fit the image, that's not taken into account. So fitting the visibilities has this advantage. And it's particularly important for sources that are very big on the sky, where you might expect a lot of signal in those shortest and not sampled UV distances. Then the visibilities have well-characterized noise properties. So the noise at every UV location should be a Gaussian with a sigma equal to what you derive from your weight. Image pixels, and they're independent of one another. So the noise in one UV point is independent of the noise at another UV point. Whereas on the other hand, if you make an image, the pixels in this image that you make are correlated with one another. And so that introduces correlated noise, and that may be difficult to account in say a fitting routine that you wanna implement for your model. Additionally, gridding and deconvolution, as David mentioned yesterday, affects images in a non-linear way, so can also create artifacts in your image. And as it says in the Thompson, Warren, and Swenson's book, fitting the image is basically fitting a model to a model. Whereas what you really want to do is fit your model to the data, which is your visibility, your sampled visibility function. Now, in practice, so this is all great, but in practice, your emission morphology may be too complicated to account with simple models, and so imaging, practically in most cases, is done first anyway. So you would first carry out some imaging see what your morphology is. And if you think that your morphology may be easily represented by simple models, then you may proceed further to, for example, fit your UV data. And but anyway, you would use imaging to first get a rough idea of what your emission structure would be. And okay, so I'm gonna briefly stop there to give you a break and to answer any questions you may have before I move on to imaging. Any questions? No questions? Jonathan.
Yeah, Luca, one thing you did was you loaded up that file of visibilities, which was a numpy file. You didn't explain how you create that thing.
Yeah. So I didn't have time to go into that. So yeah, Jonathan points out that I didn't say how I created. I didn't say how I created this file from the data that you get in Mir. So I will go into how to move data out of Mir next when I talk about imaging. But basically, how this was created is you export the data from Mir, and you read it into CASA, into a measurement set, into a CASA measurement set, which we'll look at in a moment. And then I have a routine that you can run in CASA that basically extracts all this data, all these values, UV, real imagery, and weights from the CASA MS, and puts it into a NumPy file, which is then very easy to read. So yeah, so you need some knowledge of how CASA works in this case to be able to pull out that information. But what I will do is I can make this code available. It's very simple, and I can make it available to everyone. So you can take your CASA data and extract all these UV, real imagery, and weights and play with them as you like.
Thanks.
All right. In that case, I'll get set up for a minute.